So today we're going to be measuring the kitchen range hood exhaust fan flow, and we're going to be using two tools. We're going to be using this velocity pressure pitot tube, and we're going to be using the DG700 manometer, digital manometer. So what's interesting about this is basically this pitot tube is like a static pressure pitot tube and a stagnation pressure pitot tube. So it actually has little tiny holes along the sides here that get connected to this pressure tap, and then it actually has a hole inside the tip like a stagnation pressure probe pitot tube that gets connected to this tap. Now what's interesting about this is you're going to hook this up to the DG700 gauge so that it's going to tell the difference between the static pressure and the stagnation pressure, and that's going to give us dynamic pressure, or sometimes referred to as velocity pressure. Now velocity pressure can be converted to a flow rate in feet per minute, and then that can be converted into cubic feet per minute, a volumetric flow rate, volume, when we know the diameter of the duct. So we're going to be actually going up into the attic. We're going to be drilling a hole into this straight metal kitchen range hood exhaust pipe, and we're going to insert our velocity pressure pitot tube into the duct, and we'll take a traverse reading. So we're going to insert it in, and then we're going to take 4 readings across, average those readings out, and then that will be able to give us the information we need to convert it into the kitchen range hood exhaust fan flow rate. We're inside the house, and we're looking at the kitchen exhaust hood right here. Now, code requires that the kitchen exhaust hood moves exhaust out of the house at least 100 CFM. Typically, the way they get installed, they don't move that much. Some of them will move more. We think generally you should put in 150 CFM fan if you want to actually move 100, just to be on the safe side. These things are actually source control measures. So this is going to actually control the moisture that's generated at the cooktop, and it's going to exhaust that moisture out of the house. So this is a moisture control, and its byproduct is it's also odor control. Now you'll notice that this fan here, it's actually labeled, and it's got one switch, a toggle switch up here for the light, and it's got one for the fan. And it actually has 2 settings. It's got the low setting and it has a high setting. So we test this, we want to test it in the high setting. And so I'll go ahead and turn this on, and having told the people that live here not to turn this off because we're going to go up in the attic and measure this, it would really suck if we get up there and all of a sudden somebody turns this thing off, then we have to come back down out of the attic. Since this is in Texas, and it's pretty hot in our attics, so I'd rather just make one trip up there and get in and out as fast as I can. So I'm going to go ahead and turn this on to the high setting, and then we're going to go up into the attic and we're going to measure the volume in this device. We're up in the attic, and here's the kitchen range hood exhaust vent pipe coming up from the kitchen range hood. So we're going to take our drill, and we're going to very carefully, probably not very carefully, we're going to avoid this seam because we don't want to drill anywhere near that seam right there. So I'm going to come over here, and I'm going to drill a hole through the sheet metal. Right there. And then put the drill down. And then we're going to insert our velocity pressure pitot tube into this. And we're going to measure what the velocity pressure is and convert that to a flow rate. I've inserted the velocity pressure pitot tube with the tip forced or pointed in the direction of the airflow. So it's going to measure the stagnation pressure. And so that's going on channel A is going to the stagnation pressure port, which is at the end. And then channel B is going to the static pressure port, which is coming off the side of this velocity pressure pitot tube. Now with this gauge set up in pressure mode, and with it set up in channel A and channel B mode, what I would have to do is then record these numbers and then subtract the A channel from the B channel. And that difference will give me the velocity pressure. However, if I did something a little bit different here, and I simply put them so that it's on this, now it's going to actually display the pressure difference, and it's going to record it in inches of water column. That's what I've got the gauge set up for right now. And so it's got that set up that way. Now what I would do is I would record the reading here, and then I'm going to withdraw the pitot tube out about a quarter to a third of the way through, and then I would record that value, 0.0320, and then pull it back out again, and I get 0.0312 or 336, and pull it out again. You can see it's bouncing around, and this is why you would have to take an average reading, because it's, and now I've got 0.0387, 0.04472. So you would just take these averages of these numbers, and you would add them together and divide by the number of readings that you've taken to get the average velocity pressure. Now, the other cool thing about this DG700 gauge, as I pull this velocity pressure pitot tube out again, is if I put it on this side over here, on the B side, and I change the mode from pressure, pressure, pressure flow at 50, pressure flow at 25, pressure AH, to pressure velocity, and then I, again, carefully insert this in, and lost the end of the tube here. It's a common problem when you're dealing with sweating in a hot attic. So now I insert it into here again, and this time it's going to measure and display the feet per minute. So the gauge can do all that math for me and just convert it directly, the velocity pressure directly to feet per minute. And I can take the reading there, and so I would take it and then say it's up against that edge. It's 451. Withdraw the tube, 295. Withdraw the tube, 381. Withdraw the tube, 475. 450. 525. And withdraw the tube so that it's up against this end. And I'm back to 463. Then I'll just take the average of those readings, and that will give me the feet per minute. Now, the other thing that I need to figure out here is what is the diameter of this duct. And we need to have the inside diameter. So one simple way to do it is to simply insert the pitot tube until it presses against the other side of the duct, right? Pull this out, and then measure the difference as I disassemble this. Measure from here to there, and that'll give me a really rough idea of the diameter of the duct. So let's see. Here. Pull out my handy measuring tape, which for some reason seems to be stuck. And I have a 6-inch diameter duct. So I can do the math and convert 6-inch diameter duct, round duct, to square foot number, and we'll show you how to do all that math here shortly, and convert all of that into an kitchen range hood exhaust fan flow rate. We've made a hole in this range hood, and we're going to need to close it up. Now, I'm using some tape. I know all tape fails. And the tape that I'm using is UL 181A-P, so that's duct board pressure sensitive, and pressure tape, and UL 181B-FX, so that's tape for flex duct. This is a metal duct, but since all tape fails anyway, I'm going to be confident that this will work for our purposes today, or for any purposes dealing with sealing small holes like this. So I'm going to go ahead and pull this paper backing off and seal up over that hole. Anytime you make a hole in something to do a test, you should always make sure that you've got the sealing materials to seal up the hole after you're done. Now we're going to take the average of our velocity, the feet per minute. So we had 451 plus 295. Whoop, clear. 451 plus 295 plus 381 plus 475 plus 525 plus 463 equals 2,590, and that was 6 different readings. So we'll divide that by 6. Equals 431.6666666 all the way across. So I'm going to go ahead and put that into memory and clear that out. Now the next thing we have to do is we have to calculate the surface area, the cross-sectional surface area of that 6-inch duct. So if you remember, the equation for the area of a circle is pi times the radius squared, pi r squared. So we're going to square the radius. It is a 6-inch duct, so it has a 3-inch radius. So 3 times 3 gives us 9 times pi, 3.14, whoop, 3.14. It's really helpful if you actually hit the right numbers. 3.14 equals 28.26. Now that's in square inches, and we need to convert that to square feet, so we would divide by 144 square inches in a square foot. Gives us the square footage of the cross-sectional area of a 6-inch duct is 0.19625 square feet. 0.19625. So if we recall memory, times 0.19625, it gives us a flow rate of 84.7145833 cubic feet per minute. So it gives us a flow rate of 84.7 cubic feet per minute. Now I'd probably call that 84. And so remember that this was on the high setting for the range hood, the high setting of the fan, and it should be moving 100, and it's actually moving 84 cubic feet per minute. And this is very common, that these kitchen range hoods are actually underpowered and aren't delivering what they should be delivering.